Yes. Professor Matthias Militzer, the floor is yours.
Yeah, thank you very much for the kind introduction. It's my great pleasure to give a lecture in this series. And I want to talk about advances in microstructure engineering of steels. This is an area of research I have worked in for quite some time. And I would like to give you an overview on maybe also from a historical perspective, but also what the state of the art in this particular research area is. So before we get started with the research topics, I think it's worthwhile to get an overview on the significance of high-performance steels. And I would like here to take an energy perspective. And so steels are important for energy production. We see here a picture of renewable energy, a wind farm in Denmark. And we have to keep in mind that these are dilute facilities, so we need for a wind farm 10 times more steel than in a nuclear power plant of the same capacity. Then steels are important for energy transportation, so pipelines come to mind. So that's important for a country like Canada with lots of oil and gas reserves. But we should also keep in mind that the proposed transition to hydrogen economy, we would also see different gases and fluids being transported through pipelines, so they will remain important also for many years to come. And then it's about energy end use, so construction, transportation. We see here an architectural marvel. That's the Skytree in Tokyo. That's the highest tower in the world. It's built in a seismic very active area, and high-strength steels and able to find an architectural design to build this tower. And then it's transportation. So automotive steel grades are one of the most demanding area in steel and steel grade development. And there has been a tremendous development over the past decades in introducing new steel grades in automotive design. I would like really to emphasize a little bit the area about production, transportation, and also this used in terms of steel use. These are actually plate steels, and they provide, if you want, so the backbone of the infrastructure and have an enormous significance for society. And that's maybe sometimes a little bit underappreciated. And if you look back from a more historical perspective, most of these steel plates are now produced by thermomechanically-controlled processing, so TMCP for short. And this was introduced in the 1970s, so half a century ago, and it essentially transformed steelmaking into a modern manufacturing industry. So the idea is that out of the hot mills, so plate steels are hot rolled products, the steel comes with the properties that are required for the application without doing any additional heat treatments, normalization, etc. And this means that during processing in the hot mill, the microstructure has to evolve in a way that we have the properties that we would like to see. And we have here a very schematic outline of a hot mill. So the steel slabs are reheated into the austenite region. We see austenite grain growth taking place. And then we have rough and finish rolling taking place. In the rough rolling, the idea is to get grain refinement due to recrystallization. In finish rolling, it is about having no or only limited recrystallization to get work hardened or pancaked austenite. And this has been facilitated primarily by microalloying with niobium. So I think it was in the 1960s that niobium became readily available as an alloying element for steels. And this pancaked austenite is a very good austenite conditioning for subsequent phase transformation on a runout table where austenite decomposes in ferrite or other transformation products. And this is now increasingly done by what we call accelerated cooling, so pressurized water sprays are being used, etc. And this has become a key technology in processing of plate steels, and similarly also in a hot strip mill. And basically, we want to get the right microstructure to have the right properties for the application. So we need essentially process models that are microstructure-based. And when we look back in the 1970s, 1980s, then phenomenological models were usually applied, like a Johnson-Miller-Framy-Kolmogorov model that would provide information on the fraction recrystallized, the information on phase fraction transformed during the phase transformation. And this is what we can call microstructure engineering. So this is, we want to link the operation parameters of an industrial process. So here, hot rolling, the hot mill, to the properties of the product that results from this process. So here the hot rolled steel, by accurately modeling the microstructure evolution. And now, half a century later, we have different opportunities, but it's worthwhile to do this modeling, but it's worthwhile to review what the status was maybe in the beginning of the 1990s in terms of hot rolling process models. And there was a special issue of ISIJ International in 1992 that summarized the state of the art at the time. And the volume contained 22 papers, most of them from Japan, but also some contributions from Korea and Europe, none from North America. And what was interesting, that about half these papers were authored or co-authored by steel companies, and a wide range of topics were covered in terms of grain growth, recrystallization, precipitation, phase transformation, and then the linkage via structural property relationships to the mechanical properties. And since there was a contribution from both academia and the industry, so fundamental models were presented, as well as their application to industrial rolling with an emphasis on plate rolling of high-strength low alloy steel. So these are these microlloyed steels that contain usually niobium as a microalloying element. And a summary of what was achieved is shown here by the contributions from Kern and co-workers from Germany, who basically calculated the yield strength for a range of plate steels with different thickness, different compositions, so kind of low carbon steels, microlloyed with niobium and also with vanadium. And you see what the predictive capability at the time was for, and also what the strength grades were, so between 300 and about 550 or so megapascal. And many of these steels are also still important today. So this was done 30 years ago or so, and at the time when TMCP was introduced, this also coincided with something which was, I believe, quite important for the industry. It coincided with the introduction of personal computers. So an engineer in the industry could have a computational device on his or her desk and to do some of these relatively, at the time, simple simulations. But today, of course, we can be much more sophisticated. We have seen since then a tremendous increase in computational power. And so we can do models on different length scales. So these additional models were done on what we call the macro scale. If you want to the scale of the size of the metal or the steel that is being produced, or the specimens that you have in laboratory investigations. And as I'd say, the JMAC model was maybe an important ingredient in some of these process models. But on the other hand, we know that it's the migration of interfaces between different phases or between different grains, i.e. grain boundaries, that determine the microstructure evolution, and that alloying elements tend to interact with these microphases. And if you look at an interface, it's maybe about a nanometer or so, something that happens on the atomistic length scale. And we have now the computational power to use modern computational material science tools that include tools that can atomistic scale, like density function theory, molecular dynamics, kinetic Monte Carlo, etc. And what we are really interested in is actually the scale in between, this so-called mesoscale or the scale of the microstructure, which is for steels usually in the micrometer range. So we see here a typical microstructure of a dual-phase steel. So that's a steel that is particularly important for automotive application, where in white it's ferrite, dark is martensite. And for these sort of steels, it's intercritical annealing in a continuous annealing line or hot dip galvanizing line. That is a critical processing step where we see the formation of austenite from a ferrite perlite or ferrite carbide microstructure. And what is run here in the background is a phase field simulation of this intercritical austenite formation. So the white areas, austenite, red ferrite, and these orange particles are carbides. And if you look at next generation process models, we probably would like to predict some sort of a microstructure rather than just a phase fraction or mean grain size. And maybe what is even more important, to incorporate in a quantitative way the role of alloy composition, and there the atomistic scale simulations might be very useful. Okay, so if you look at what happens on the scale of the interaction of solutes with the interface, and I'd say that niobium is a particularly important microalloying element. We have now both experimental tools as well as the modeling tools to deal with atomistic resolution. And what is shown here is a 3D atom probe result of niobium segregation at the alpha-gamma interface. So that's work by Dong and co-workers at Tohoku University. So kind of for model alloy with 0.035 weight percent niobium. And if you look at steels of relevance, so we look a lot in line pipe steel. We have here an X80 line pipe chemistry that also has essentially a similar amount of niobium microalloying. And of course, there's a few other elements, the chemistry a little bit more complicated. And we were able to conduct experimental studies where we had an austenite grain size, here 80 micrometers, so that's relevant for the heat affected zone, which is important for the weld heat affected zone, is important for the integrity of a pipeline construction. And we were able to do a preheat treatment, in one case to have niobium precipitated, in the other case most of the niobium in solution. And what we see here is basically the fraction transformed as a function of temperature for a cooling rate of 30 degrees per second. And you see that there's a shift in transformation temperatures by about 50 degrees when niobium is in solution. So it kind of affects the migration rate of these alpha-gamma interfaces. And the transformation products are very different. So for the higher transformation temperature, we see something that we call upper bainite with a low density of high-angle boundaries, versus when we reduce the transformation temperature, we get what we typically call lower bainite with a high density of high-angle boundaries. And that's actually the preferred structure for the coarse-grained heat-affected zone in these steels. What we have to realize, of course, that solid segregation on a nanometer scale and is a very different length scale, the microstructure evolution, where we are on a micrometer scale. So what can we do to address these different length scales? So we can do first atomistic scale simulation, and the starting point is more increasingly ab initio density functional theory. An example is shown here for an alpha-gamma interface in iron. The typical code that people now use is VAST, Vienna Ab Initio Simulation Package, probably the most advanced code in the DFT calculation area. We have to keep in mind it's a ground state theory, so we are at 0 Kelvin. It's computational very expensive, so even with our much developed computational resources, we typically can only do calculations with a few hundred atoms. If you want to have periodic boundary conditions and an interface in the simulation domain, we have to find special interfaces that have a periodicity that fits into the simulation box. And here for the alpha-gamma interface, we found a quantum of Sachs orientation relationship that fulfills these criteria. If you look at grain boundaries, we typically are restricted to low sigma grain boundaries, sigma 5, sigma 13, etc. And then if we look at iron, there's a few challenges associated because we have to account for the magnetic state of iron. So that's not really a big deal in BCC iron, which is ferromagnetic. We can do spin polarized calculations, very well established. It's a little bit more challenging for the FCC grain that should be paramagnetic. And we have to find approximation for the paramagnetic state. An example is shown here with the double layer antiferromagnetic structure. So blue and red positions are spin up, spin down, respectively. Another approach is what is called special quasi-random structures that can be used. So there's a few different options that one has. And what we do is with these simulations, we basically put a solute atom in the simulation box, calculate the energy, put the solute at the different positions, recalculate the energy, and so on and so forth. And in this way, we can map out the energy landscape of the solute atom across the interface. And we have done so for a few important alloying elements in steel. And I show you a result for the all-important microalloying element niobium, as well as of manganese. That is also an alloying element that we find essentially in all steels. And what we see is for niobium, we have indeed kind of an energy value dip in the energy landscape across the interface. What we also see is that different approximations for the paramagnetic state have little influence on the calculated energy level. And we also confirmed that niobium is thermodynamically a ferrite stabilizer, so the energy level at the BCC side of the interface is lower than on the FCC side. Manganese, on the other hand, is an austenite stabilizer, so it's the other way around. FCC has the lower energy level compared to BCC, and we have also a little bit of a potential drop here at the interface, not as pronounced as for niobium, though. Now, the question is, what do we do with these sort of data that we have? So we basically know the binding energy to each individual site at the interface. And we can argue, we can use these binding energies to estimate what the probability is that a particular interface site is occupied at higher temperature. And out of this, we can basically estimate what the enrichment of the solute of this alloying element and the interface would be as a function of temperature. And one can, for the austenite decomposition, the temperature range that is of interest is typically 500 to 800 degrees Celsius. And one can introduce an enrichment factor that is here expressed with a very simple exponential expression where EB in the exponent is a representative binding energy that is now plotted here as a function of the solute volume. The dashed line is the solute, is the volume of the iron atom. And then we see niobium and also molybdenum tower upwards here in the right-hand area as a much larger solutes that basically promotes their segregation to interfaces where there's excess volume. So it kind of reduces the misfit that these atoms see in the bulk lattice. And then we have atoms with similar size to iron, like manganese, silicon, chromium, and they still have an appreciable binding energy, and different considerations we'll have to make for these elements. So silicon has a very different electronic structure than the transition metals. Manganese and chromium prefer an antiferromagnetic ordering, and so they may see something that we call magnetic frustration in an otherwise ferromagnetic system. What is important to realize that the enrichment factor that we predict can be compared with experimental data from the 3D atom probe studies, and where we can basically translate back the concentrations that were measured into representative binding energy. And we did this too for a study that was done for a number of years ago by Van Landerhem and for a number of these alloying elements. And what we did see that the experimental binding energies compare very well with the DFT concluded binding energies. The alloy trends are reasonably represented, and even the absolute numbers are very, very similar. And that's a very encouraging result. I should also say that very similar trends in the binding energies we would see when we just consider a sigma 5 grain boundary in BCC iron, which is a much simpler simulations because we don't have to worry about this approximation for the paramagnetic state. Okay, 0 Kelvin, nothing moves. If we want to have a moving boundary, we have to move on to maybe molecular dynamics as a technique that can be used. And with molecular dynamics, there's a number of challenges. Challenging number one is we have empirical potentials that may not exactly describe the material that we are interested in. The other challenge is we are on the time scale of atomic vibrations. So the simulation that we can do is in the order of nanoseconds in terms of microstructure evolution, if you want, so tens, hundreds of nanoseconds. We look here at an alpha-gamma interface in an iron-carbon alloy. And basically what we use is the potential of Henriksen and Nordlund that creates what looks like a reasonable iron-carbon phase diagram when we are considering the two-phase field austenite ferrite. If you look very careful, the temperature scale is in Kelvin. Pure iron is predicted to have the equilibrium transformation temperature of about 750 Kelvin, which is much different from the actual transformation in pure iron. May this be, maybe we can still learn something out of these simulations. We can heat up our specimen that is shown here with an austenite film at the bottom and ferrite on the top in blue. The white, large white dots represent carbon atoms. So we go into the austenite phase field. And what we see is that the austenite grows, consumes ferrite. Initially, the interface moves very quickly. And then it seems to come to a little bit of a standstill. But we see also that we get an increased enrichment of carbon at the interface. And the atoms still jump around at the apparently stationary interface. So there's two observations here that probably for many of our steels that we are considering, it's the interface moves with carbon enrichment, and that's also confirmed with the atom probe tomography results that we obviously see an enrichment of carbon at interfaces, including grain boundaries. And when we have just the transformation time here of 16 nanoseconds, even though carbon diffuses very quickly, it doesn't diffuse quick enough to have substantial motion diffusion distances in a few nanoseconds. What I should mention here also, this is an area where we are increasingly engaged in machine learning. So one thing is, I mean, there's a lot of effort being done to develop potentials for molecular dynamics with DFT quality. So the machine learned interaction potentials is an important area of work right now. And the other thing is also maybe analyzing the jump in and jump out of atoms of an interface to get information on the mobility. And here also machine learning tools could be very useful. And that's also an area of significant research at the present time. Okay, now we have all this atomistic simulation data. What can we do with them? And basically, the idea is, let us say, if you look at phase field simulation, you run the grain growth simulation in the background. We need interface properties to populate the phase field model. And maybe we can use information from atomistic simulations to find these properties, or at least some of those, and then use DFT data to develop at least trend predictions in terms of alloy development for grain growth, recrystallization, and phase transformation. And what we propose here, I would like to illustrate on a case study that deals with grain boundary migration during recrystallization of gold. It has nothing to do with steel, obviously. And we go back to an experiment that was done by Grünwald and Hessner also half a century ago. So they started recrystallization in ultra pure gold that contained bismuth and iron impurities on the ppm level. They found that there's a particular grain boundary that is moving during the recrystallization process. And this is a sigma 13 grain boundary, which we can actually put into a DFT box. Now, what Grünwald and Hessner found, they measured the velocity of this grain boundary at different temperatures and then made an Arrhenius plot and did see deviations from a classical Arrhenius behavior. And so there's two Arrhenius branches, one at higher temperature, one at lower temperature. And the argumentation was, well, at higher temperature, the grain boundary moves without solute interaction. At lower temperature, there's an interactions with the solutes. And then we have a transition range. We can extrapolate the high velocity branch to lower temperature. And the velocity difference that we see here can be interpreted as the effect of the solutes in terms of solute drag. If you look at the velocity of the boundary, it's the boundary mobility times the effective driving pressure, which is in this particular case, the driving pressure of recrystallization due to the stored dislocation density. And that's reduced by a solute drag pressure. Now, what we can do with DFT, we can basically calculate, well, what the binding energies of bismuth and iron at the boundary will be. We found that it's bismuth that segregates rather than iron. We calculated the binding energies for each individual site at the boundary, and then calculated or estimated what the probability of occupancy of these individual sites is at the temperatures of interest where the recrystallization takes place. And we can, out of this, determine, based on the DFT simulations, what we expect as enrichment here of bismuth at the interface, so basically in atoms per square nanometer. And then we can use the classical solid drag model, Kahn, Lücke, Stüve. They assume a very simple potential well at the interface, this triangular-shaped potential well with a depth of E naught, which is the representative binding energy. We can calculate in this solid drag model what the enrichment as a function of the E naught value will be. And then we can say, well, we set these two enrichment factors equal. And out of this, we can estimate from the DFT data what the depth of this potential well in Kahn's solid drag model should be. We get values between 0.6 and 0.7 EV. And if you just do the classical fit of the experimental data to the solid drag model, we get very similar values for E naught, also between 0.6 and 0.7 EV. And I should say that this variability that we see is primarily related to what driving pressure we have assumed for recrystallization. There's obviously a little bit uncertainty. We have an order of magnitude approximation for this driving pressure, but not an exact number. In considering all these uncertainties from experiments and simulations, the range of parameters from both analyses are consistent. And again, this is a very encouraging result. And we use this approach now to make alloy predictions. And I will show you some results for austenite grain growth in steels. Ito and Zawada from Nippon Steel had done a wide range of simulations for different sigma boundaries in FCC iron to find out what the binding energy of important alloy elements in steels would be. I show you here results for sigma 5 grain boundary with niobium, titanium, molybdenum, vanadium, and manganese. So these are binary systems that are being considered. And that's the order of the depth of the potential well. So niobium has the strongest binding energy, followed by titanium, molybdenum, vanadium, and manganese. And then we use this concept that I just had illustrated for gold to calculate the effective value of this binding energy in Kahn's solid drag model here at 1,000 degrees. We see the trends that we see for sigma 5 boundaries are replicated in terms of the alloying elements. For different sigma boundaries, there's a little bit variability when we have different sigma boundaries for a given alloying element. But for trend predictions, basically, even the sigma 5 grain bond is representative. And what runs here in the background are grain growth simulations from phase field simulations, one with a niobium content of 0.01 atomic percent, one with manganese 0.1 atomic percent. So these are actually composition relatively close what we would find in interstitial free steels, another workhorse material for automotive application. And clearly see that adding a little bit niobium is much more efficient in reducing grain growth rates than the manganese addition. And one can do these simulations now for different compositions, different temperatures. And what we found is we can introduce a representative solid drag parameter, that's the enrichment divided by diffusivity, to describe the reduction or the change in grain size evolution with respect to a benchmark where there is no solute in the simulation domain, so pure iron. And in this solid drag parameter, the diffusivity, we can actually approximate with bulk diffusivity. They are relatively well known for iron because the diffusivity across the grain bond area, which is relevant, typically scales with the bulk diffusivity. So we can compare now this solid drag parameter with a solid retardation parameter that was concluded from very careful studies in recrystallization kinetics also some 40 years ago by Akben and co-workers. And we see that the ranking is consistent with these experimental data: niobium, strongest solid drag element, followed by titanium, molybdenum, vanadium, and manganese. Okay, now doing experiment is quite involved, even with advanced experimental and high throughput techniques, but it's comparatively straightforward to go for the periodic table of elements with DFT simulations. And that's shown here. So it's the sigma 5 grain bond there in BCC iron that is considered. And then for an alloy composition of 0.1 atomic percent, the enrichment at 700 degrees Celsius is shown here. Dark green means high enrichment, light green less enrichment, white virtually no enrichment for these elements, and elements shown in gray were not considered. And what we see is that niobium is only a lightish gray, so it's not really the strongest segregant, if you want to, compared to other elements in the periodic table. And one can now use this maybe to consider which of these elements could be of interest for a new alloy design. But the other aspect that's important also, what impurities, what residuals could be of significance. And if you look here, this area, particularly with tin and antimony, bismuth, very strong segregants. And this becomes increasingly important with the current paradigm shift in steel making. So we have a change from blast furnace, basic oxygen furnace steel making to increasingly electric arc furnace steel making. And really the driving pressure is to reduce greenhouse gas emissions. And the steel industry contributes about 8% of greenhouse gas emissions worldwide. And if you look at the blast furnace BOF steel making route, that's really the production of carbon dioxide. And this is the major contribution to the greenhouse gas emissions from the steel industry. And this could be avoided by doing steel making with electric arc furnace processes. So about 50% or even more reduction greenhouse gas emission is proposed or projected. And then we use a lot of steel scrap in EAF steel making. So this promotes also a circular economy. But scrap contains impurities or residuals that are difficult to remove. Maybe the most important one of that being discussed is copper and tin. And if you look at the values in dirty scrap, we have upwards to 0.4 weight% copper and 0.02 weight% tin. And in clean scrap, maybe it's a factor of 2 or so lower, but nevertheless, it is still being present. There's basically EAF steelmaking is an established technology. It's particularly used also in North America. And I think right now a quarter of the steel is made with EAF steelmaking. So it's an established and cost-efficient method. And in particular for copper, there's strategies to mitigate adverse effects in terms of hot shortness by adding nickel. Maybe less so is known about tin, that is very active in terms of segregating to grain boundaries and interfaces. I think there's some evidence also from this that's being used in electrical steels. MADES-SB, we need to account for the role of the residuals, and maybe potentially new alloying concepts are required to mitigate some of the concerns that may result from the presence of a higher residual or trace element level. So we have recently engaged in collaboration with colleagues in Austria at the University in Leoben by Kern and co-workers, looking at austenite grain growth in iron model alloys, where it surfaced that residuals can be very important. What they do is they do in situ measurement of austenite grain growth using high temperature laser scanning confocal microscopy, so a typical microstructure shown here. And they started off with electrolytic iron that contains sulfur, phosphorus, and carbon as trace elements or residuals, if you want, so on the ppm level. And they were very excited about their results. They found parabolic grain growth, and this was representative in the first look for grain growth in pure iron. Then they also did do grain growth studies in iron carbon alloys, here 0.3 weight% carbon being added. And what they found out that adding carbon increases the grain growth rates. So maybe by a factor of 2. So after 20 minutes of holding, the grain sizes are summarized here. So we have to keep in mind the scale here is from 0 to 300 micrometer, here from 0 to 500 micrometer. So we reanalyzed these data and basically used the data for the iron carbon system to extract an effective intrinsic mobility. And what I mean with effective, it's not the classical intrinsic mobility for pure iron. It's the mobility of the grain boundary that carries the carbon atoms. So very much what I had shown just earlier today in terms of the molecular dynamics simulation that carbon would enrich at the migrating interface. And based on this intrinsic mobility provides then the starting point to account for which impurities may actually reduce the grain growth rates in electrolytic iron. And we can do the DFT calculations for binding energies at the sigma 5 boundary in FCC iron. And we see that sulfur is the element with the highest binding energy, followed by phosphorus and then carbon. And what is important to realize that the sites that are called I1, I2, these are interstitial sites at the boundary. And sulfur and phosphorus, even though they are substitutional alloying elements, at the grain boundary, they prefer to segregate to the interstitial site. So they compete with carbon that obviously only segregates to interstitial sites. And when we look a little bit closer in what happens with sulfur, when sulfur occupies an interstitial site, it essentially eliminates segregation to the substitution sites or reduces the binding energy to these sites quite significantly. And so it's really the competition of carbon and sulfur and to some degree phosphorus for the interstitial segregation position. So if you do the analysis now for this electrolytic iron with whatever the 31 ppm sulfur, what we found is that the enrichment at the temperatures of interest is that this interstitial site is usually occupied, and we get a grain boundary enrichment of sulfur that is predicted to be 5 atoms per square nanometer. And then we can do the analysis for describing the grain growth behavior. We know the enrichment, or the, if you want to, the effective binding energy of sulfur for this interface, for this grain boundary. We know the intrinsic or the mobility of moving the boundary without the sulfur interaction. And then the unknown to find is to replicate what we see in grain growth is to find the diffusivity of sulfur across the grain boundary. And if we do this, we see that this diffusivity scales with the bulk diffusivity of sulfur. It's maybe a little bit smaller. This is maybe at first look a little bit surprising because we always think that at grain boundaries, these are fast diffusion paths. But there's increasing evidence that it's not true for interstitial elements. And since interstitial sites are involved here, it's maybe quite reasonable that the diffusivity of sulfur across the grain boundary is by a factor of 2 or so smaller than the bulk diffusivity. And then Kern and co-workers recently engaged in a study where they put phosphorus into their model alloys, and this was recently published, so that's from their publication, and they had increased the phosphorus level from the 36 ppm material, the electrolytic iron, to almost 1000 ppm, and they found what was expected. Adding phosphorus would delay grain growth, reduce the grain growth rates, and we can do here a very similar solid drag analysis. Now it's the competition between sulfur and phosphorus for segregation. And what we found is that, well, sulfur is still segregating to this interstitial site, like in the electrolytic iron, but now increasing the phosphorus content, phosphorus can occupy additional sites in the grain boundary, and this increases obviously with the phosphorus bulk content. And now we have to find out, well, how phosphorus fusion could affect the migration of the interface or the grain boundaries. And we have to keep in mind that diffusivity of phosphorus is actually lower than of sulfur, and the slowest diffusing species is what determines. And in our analysis, we found that for all phosphorus contents and temperature, we get kind of one diffusivity, again, scales with the bulk diffusivity, maybe an order of magnitude smaller. So again, it's very similar than what I had just discussed for sulfur, that maybe this diffusion involving interstitial sites plays a role as well in having a lower diffusivity across the grain boundary as compared to bulk diffusivity. And we have also to keep in mind that obviously there's a lot of assumptions are made in all of these modeling, and there's also experimental errors involved in the grain size measurements, etc. So getting some sort of a consistent diffusivity is actually quite appreciable result here. Okay, so that's maybe an review how we can deal with the effect of impurities, trace elements, or residuals, whatever you want to call them, to see the effect on grain growth here, microstructure features. And grain growth is a relatively important measure to with this, to get an idea about role of alloying elements or impurities on microstructure evolution. And these sort of studies can now be extended maybe also to the residues that are of interest from EAF steelmaking, tin, antimony, etc. Okay, now I would like to use a couple of minutes to talk about another technique that can be used to make austenite grain size measurement. That's laser ultrasonics for metallurgy, or for short LUMET, that we have in our laboratory as an attachment to a Keeble thermomechanical simulator. And what is basically happening here is we have two lasers, a generation laser that ablates the surface of the specimen, creates a broad ultrasound pulse wave that travels through the specimen, and the outcoming wave is detected by a second laser. And we get waveforms, we get these compressive signals, we have a delay time between the signals, and we see also that the amplitude is decreasing. So attenuation is another measurement result. And the attenuation spectrum is a function of frequency, can relate it to the grain size. So this factor B is grain size dependent. And then the velocity is obtained from the delay time, because we know the thickness of the specimen, and the velocity is related to the elastic properties of the material. So here, when the elastic properties change, there is a texture change during recrystallization or phase transformation, we can record this as well. And we did do a high throughput studies for line pipe steels, where we looked particular for conditions relevant for the coarse-grained heat-affected zone. We see here typical line pipe chemistry, so low carbon steels, microlloyed with niobium and also titanium, containing manganese, molybdenum, chromium at various levels. And we do a classical heat treatment study, heating at 50 degrees per second to a holding temperature of 100 degrees, where we kept for 90 seconds. And it kind of replicated what we would maybe assume to be happening when we go very close to the melting temperature, where the peak time, holding time, if you want, is maybe a second or so. And we see initial rapid grain growth, and then we see that we get into a limiting grain size. So that's related to the presence of titanium nitrides that are strategically added to these line pipe steels to minimize austenite grain growth. And then some of the grain growth occurs during the heating stage. And at around 1100 degrees Celsius, we assume that niobium carbides would go in dissolution. So this leads also to an apparent increase in the grain growth rate, reduced pinning from the niobium carbides. And you see that with one test, you get hundreds of measurement points. We validate now and then these measurement data with excido microscopy, either optical, classical optical microscopy, or now increasingly using reconstruction of the austenite structure from EBSD mapping. And once we have done one test, we can do a second test, a different steel, and a third test, etc. And I show you here 6 tests, and this is what you can do basically in an afternoon. And you can compare this now, how long it would take to create even portions of these curves with classical ex situ grain growth studies. What we see is we see quite a different range of the limiting grain size between maybe 50 and 100 micrometer. And we have here steels labeled with L. These are laboratory produced steels, so they are ingot cast. And then with I, these steels are industrial produced, continuously cast. And this obviously has an important impact on the titanium nitride particle distribution. And we get finer titanium nitrides in these industrial produced materials. And have confirmed this also with selected electron microscopy studies. Now we can describe this classical grain growth behavior. So the initial portion depends primarily on the mobility of the boundary, the limiting grain size on the presence of the titanium nitrides, very classical grain growth equations being used, where the classical parabolic grain growth is mitigated by this pinning term from the titanium nitrides that is related to the volume fraction of these precipitates at their mean size. And the volume fraction can be determined with Kalfa databases, and some electron microscopy was done to verify that this limiting grain size is consistent with this approach. The mobility depends on temperature. One assumes typically an Arrhenius behavior for these line pipe steels. It had been shown that the apparent activation energy of 350 kilojoule per mole is a reasonable assumption. And then we have just the pre-exponential term as a fitting parameter. And we found that the mobility, the apparent mobility, decreases with adding carbon and with niobium in solution. So niobium in solution, that's consistent with our DFT analysis, showing niobium as a strong segregating element. The role of carbon seems to be inconsistent with what I had just shown for these model alloys, but we have here to consider that carbon interacts with many alloying elements, for instance, manganese, and it could be that it kind of leads to some co-segregation of these additional substitution elements, and that's actually the reason why we see this apparent effect of carbon in terms of reducing the effective mobility of the boundaries. Okay, with this, maybe it's time to come to some conclusions. We have well-established microstructure process models using this classical phenomenological state variable approach and this is widely used with success, not only in the steel industry, but also other metals producing industries. We propose here an interface-based alloy design approach where we combine atomistic scale simulation with phenomenological mesoscale simulations, in particular phase field, which is also a powerful methodology to deal with complex morphologies in the microstructure, like in bainite. Excuse me. And then we can make alloy trend prediction for grain growth, recrystallization, and phase transformation. And there's a number of challenging remaining that I haven't really touched on: nucleation, complex transformation products like bainite, how to deal with multi-component systems, including the role of residuals. With this, I would like to conclude, and thank you very much for your attention.
Thank you very much, Professor Matthias Militzer from the University of British Columbia in Canada.